This is the third part of my lecture on sampling, in which I'm going to be looking more carefully at the sampling error. We've already seen that the sample mean is the best estimate available of the population mean, but unfortunately it's not exactly the same. The difference between the population mean, shown by the yellow arrow in the distribution here, and the sample mean, shown by the purple arrow, is the sampling error. The sampling error may be positive or negative. That means that the sample mean may either be greater than the population mean or less than the population mean. But on average the sampling error is 0, because on average the population mean and the sample mean are the same. But what we'd really like to know is how much does the sampling error vary? In other words, what is the standard deviation of the sampling error? Well, if we go back and look at the data that we met in the first part of this lecture on age of our patients, we already saw that if we took a sample size of 20 out of our 100 patients, then we had 5 different samples with means of 46.1, 51.9, 52.0, 48.5 and 51.3. Now the sampling error is the difference between the sample mean and the population mean, and we know that for this group the population mean is exactly 50. So if we take 50 from each of these sample means, then the sampling error for the first sample, 46.1 minus 50, is minus 3.9. The second sample has a sampling error of plus 1.9, the third is plus 2.0, the fourth minus 1.5, and the fifth is plus 1.3. So you can see some of those sampling errors are positive and some are negative. In fact, if we take the average of those 5 sampling errors, it comes out to be a mean sampling error of 0. That confirms what we said before, that on average the sampling error is 0. But the standard deviation of those 5 sampling errors turns out to be 2.3. So that's a measure of the magnitude of the variation in our sampling error from the sample size of 20. If we do the same thing for a sample size of 10, then we had 10 samples with different means, and if we take 50 away from each of those means, then we get the sampling errors. The average of those sampling errors, the mean sampling error, once again is 0. And if we take the standard deviation of those sampling errors, it turns out that is now 3.5, a bit bigger than what we had with a sample size of 20. If we go down to a sample size of 5, we've now got 20 samples with different means. We subtract 50 from each of those means and we get 20 different sampling errors. The average of those, the mean sampling error, again turns out to be 0, but now the standard deviation of the sampling error turns out to be 4.2, which is bigger again. So we can summarise what we've got so far. For our sample size of 20, 10 or 15, the sample standard deviation, which we calculated originally in the first part of this lecture, was 10.1, 9.7 or 9.1. And we've just worked out that the standard deviation of the sampling error is 2.3, 3.5 or 4.2. So we can immediately see from that that the variation in sampling error, the standard deviation of the sampling error, is always less than the sample standard deviation. And also, as the sample size increases, that is, we are moving up the columns in this table, as the sample size increases, the variation in sampling error gets smaller. That means that larger samples give a more reliable estimate of the population mean, but larger samples gives a smaller standard deviation of the sampling error. There's a quantity called the standard error of the mean, which is very useful in measuring this. The standard error of the mean, abbreviated to SEM, is just a measure of the likely sampling error. is defined by SEM is the population standard deviation SP divided by the square root of the number in the sample NS. The problem is that the population standard deviation SP may well be unknown. So even though we know the sample size, we can't calculate this necessarily. But if you remember, we've already shown that the population standard deviation can be estimated from the sample standard deviation SS if we multiply by the Bessel correction, root NS over NS minus 1. So if we put that into this equation, we can deduce that the standard error of the mean is approximately equal to this sample standard deviation divided by root NS minus 1. And that can be estimated from the sample, because we only need to know the sample standard deviation, not the population standard deviation. So you see we've got two formulae for the standard error of the mean. One relating it to the population standard deviation divided by root n, and one to the sample standard deviation divided by root n minus 1. So we can see from both of those that the standard error of the mean is less than both the population standard deviation and the sample standard deviation, because we divide by root n or root n minus 1. So as the sample size increases, that is, n gets bigger, the standard error of the mean will decrease. That means that our result becomes less uncertain. We are more confident in the result if n is large, because we have a smaller standard error of the mean. So the standard error of the mean is a very useful concept. Let's illustrate it by going back to our age data again. We've seen that for our three different sample sizes we've got a sample standard deviation that we calculated in the first part of the lecture, and we know to calculate the standard error of the mean we need to divide by root n minus 1, which means we divide by either root 19 or root 9 or root 4 for these three different sample sizes. So if we take our 10.1 sample standard deviation, that gives a standard error of the mean of 2.3, 9.7 gives 3.2, and 9.1 gives 4.5. We've already just calculated the standard deviation of the sampling error, and we see that the standard error of the mean is a very good estimate of the likely sampling error. So how can we apply that? Well, if we take measurements from a sample of size ns, drawn from a large population with an unknown mean, then we would calculate the sample mean ms and the sample standard deviation ss. From that we can calculate the standard error of the mean by dividing the sample standard deviation by root n minus 1. Now we know that our best estimate of the population mean is ms, and if we quote it as ms plus or minus the standard error of the mean, then what we're saying there is the population mean is most likely to be ms, but it could lie above or below that by an amount relating to the standard error of the mean. That is the likely variation in our estimate. That leads us to confidence intervals, because we use confidence intervals to interpret the meaning of this statement ms plus or minus the standard error of the mean. If we got a large sample, for example n more than about 30, then the sampling error turns out to be normally distributed. That's actually an application of the central limit theorem, which we mentioned in the lecture on probability distributions. And if we've got a normal distribution, we can say that 95% of our measurements are within 2 standard deviations. So in this case we can say we're 95% confident that our result lies within plus or minus 2 times the standard error of the mean around the mean that we've quoted. We can also say that we're 99% confident that the result lies within plus or minus 2.6 times the standard error of the mean, or 99.7% confident that it lies within plus or minus 3 times the standard error of the mean. Those are all things that come from the shape of the normal distribution. If we have less than 30 measurements in our sample, which classifies as a small sample, then we saw when we talked about probability distributions that we have to replace the normal distribution with student's t distribution. And then the confidence limits depend on the degrees of freedom, and typically the number of degrees of freedom is just n, the number of measurements, minus 1. And the t distribution is generally wider than the normal distribution, so our confidence limits have to be extended a bit. We're not quite so sure if our sample is small or large. But that's the beauty of the standard error of the mean. We don't have to quote just one result, the mean. We can quote an error on it, an uncertainty, and that is what the standard error of the mean is. The standard error of the mean is sometimes just called the standard error. Standard error and standard error of the mean are really just the same thing. But the standard error is a measure of the possible error in our result. As we said, it is an indication of how close the true population mean lies to the mean that we've just calculated from the sample. It gives the confidence limits for our result. As we've seen, taking a larger sample size will reduce the standard error by a factor of 1 over root n minus 1 compared with the sample standard deviation. So for example, for 5 measurements where n is 5, that gives a factor of 1 over square root of 4, which is a half, so it reduces the standard error by a half. For 10 measurements we get a reduction by a factor of 1 over root 9, or a third, and for 50 measurements 1 over root 49, which is a seventh. Now remember the confusion about n and n minus 1? Let's just revisit that, because we've seen that the standard error of the mean can be defined as the population standard deviation divided by the square root of n, or equivalently the sample standard deviation divided by the square root of n minus 1. And if you go back to the formula for calculating standard deviation as sigma x minus m squared, it has a root n in the denominator, and if we add the extra n minus 1 to calculate the standard error of the mean, we see that the formula for standard error has got both an n and an n minus 1 in the denominator. So in Excel, if you're going to calculate the standard deviation using the formula stdevp, which is my preference for doing things, then it's already included a root n in that stdevp formula, because what it does is calculate using sigma x minus m squared over n. So it calculates the sample standard deviation despite the fact that there's a p at the end of the function name. Don't blame me for that, blame Microsoft. So if it's already included a root n, then all you have to do is to divide by another root n minus 1 to get the standard error of the mean. On the other hand, if you calculate the standard deviation using stdev, it's already included a root n minus 1 because it tries to give an estimate of the population standard deviation based on the sample. So to get the standard error of the mean, you only need to divide by another root n, because it's put in the root n minus 1 for you. So as long as you have a root n and a root n minus 1, then you can calculate the standard error of the mean by either root. That brings us to the end of the third part of my lecture on sampling. In the next part we'll look at how these can be applied to measurement errors with a practical example.